homeworks here. Why don't you just start passing those around? It's homework 5. I have a few projects here too. Yes. Yeah. Okay. Alrighty, let's roll them. Roll them. Okay. Yeah, so just pass around. Yeah, we have passed around homework 5. We'll try to get, hopefully, the rest of the homeworks out on the next lecture. Okay. When we sit down, we'll just pass them around. Just everybody sit down. We can pass them. Eventually get to them. Okay. So at the end of class today, we're going to do the Eta Kappa Nu surveys. And so someone is the surveyor here? Okay. Guess if you see that person show up, tell them to remind me to stop. I mean, so I do it. Otherwise, I'll just not do it. So I forget. So we'll stop 10 minutes earlier. So we'll do that. Okay. In office hours today, we had a couple of good, interesting issues. One issue came up in the accuracy of SPICE, and we'll get a news group comment on that. But SPICE, actually, when you start asking for very fine results, I mean, when you do your settling, right, and the 0.1% ends up, the amount of error that we're talking about is in the tens of microvolts kind of number. So you need to make sure SPICE is more accurate than that. SPICE actually, and there's a control of that in one of the parameter files that you need to put in. Particularly if you see your answer do something like, starts to kind of oscillate around like this. I mean, this can be ringing, and then it can sort of, when it finally gets really small, it can just keep on sort of jumping around a little bit. Well, what this can be is due to SPICE. I mean, SPICE actually is it's an iterative solution, right? And so it will, in the end, potentially not. I mean, there's a spec you give it on how accurately you ask SPICE to operate or to calculate to, and it keeps iterating until it. Basically, what SPICE does, it looks back at its last answer. It sees if things have changed by a certain amount. If it's changed by less than an error tolerance, then it says it's converged. So it just looks for convergence by seeing how big this final wiggles are. So it always is jumping back and forth a little bit. The question is jumping back and forth small enough relative to what your accuracy requirement is, okay? And that tolerance you should make like 10 to 100 times smaller than what absolute value you're kind of interested in having. So there's a spec that we're going to put on the news group soon today, and to help you do that, because some of you are having some weirdness occur. For example, the static settling should not be a function of any capacitors, right? Static settling means after everything's come out to DC value, all the capacitors will be open circuit then, so there's no effect, with capacitance. So some of you were seeing, well, geez, the static settling would change with the capacitor value. What was really happening was it was the accuracy of SPICE was being, working up against the limits of that. Okay, so that's one point. The other points today, let's see. Oh yeah, okay. The test benches are meant for two reasons. There's two purposes to have test benches. One is to show you how to use dot measure and test bench-like things to automate your characterization process. And of course, they're particularly important for us because we use those for grading. Okay, so so it's grading purposes. It's useful for you to see how the test benches can be worked and how to make use of them. But what you should not do is use those as your only design, output. They're really meant to sort of facilitate a little bit of automation. But really what you should use when you're trying to evaluate what's going on with your circuit, first, for the open loop case, okay, what you should do is plot the magnitude, and phase, okay. Look at those phase plots and see what's going on. So the Bode plots. Look at the whole Bode plot. We have a test bench for you that calculates the phase margin. That's kind of a thing to just help you out a little bit. What you really want to look at is look exactly at the magnitude and phase plots and see what's going on at gain equals 1. Okay, see how much phase margin you have. See what this frequency response is doing. See what these poles and zeros are doing. That's really much more useful. I mean, after you get close and the circuit's sort of working, then you can sort of automate things a little bit because you're finding sort of tweaking the thing a little bit, right? Then you kind of know the circuit's kind of working normally. Because what can happen is the circuit may be way off, working in a very strange mode. That test bench, they're not written robustly enough to determine that you've got some real screwball stuff going on. It's going to give out a number, and it just may be a coincidence. It happens to be a good number. Okay, it may not be any good number at all. So don't rely on those test benches as a primary mechanism to see how well your circuit's working, or to calculate phase margin or anything else. Okay, use magnitude and phase, and for the final FOM, as you're figuring it out, look at the transient response. I mean, look at how this thing looks. I mean, see that if it's ringing, if it's ringing like that, if it's ringing, right? Trying to there's slew rate, there's part of it. There's the small signal settling part of it. Look and see what's really going on. Is it rippling a lot like this? That means your phase margin's probably too small. If it's coming up really slowly, maybe your phase margin's maybe too large. If it's slewing really slowly, maybe your slew rate's too small. You got to put some more effort into that. So look at the actual time response and see what's going on. Then towards the end, start using the test benches, like I say, for small amounts of tweaking. The other thing was, when you're doing the open loop response, okay, the early stages of this, before you close the loop, okay, you're going to be very sensitive, because you have a lot of gain in these circuits, you'll be very sensitive to the offset voltage, okay? This little offset voltage which sets the output to 0 volts. I mean, early on we have this thing open loop, okay? here's your V in, here's your V out. The response is going to be something, you know, if this is V in versus V out on let's put it on a 10th volt scale, okay, 100, you know, 0.2, 0.3, so this is kind of going from 1 volt, half a volt, minus half volt, plus half a volt. This response is going to look like this. I mean, if you got a gain of 10,000 or 20,000, it's going to be just a really sharp, you know, transition. And it may not be right at 0 volts. This may be 0 right here. Your job is to do a sweep like this, a V in versus V out, a DC sweep. Find this response. This is too sharp to figure out exactly where this is happening. Blow it up. Do it again. And then it'll finally begin to look like this. Then you can go in there and see, here's V out on this axis here. You go out there and you find out what V in is for V out equal to 0 volts. And you can bias this thing up so that the output is biased appropriately right. And that means your DC biasing will be okay, or well as it's going to get. Okay? Now, if you don't get a curve like this, that means there's no voltage that's going to work, okay, on the input. So you got another problem, okay? But if you see this kind of transition, find out where this is. You're allowed up to a millivolt of offset voltage in your final design, okay? So, I mean, so certainly make use of that when you're doing your analysis. The way this actually works in real life, of course, is that once you put this circuit into feedback, then you don't have to precisely develop this voltage. This means this input voltage can be offset by a millivolt or so. Well, it's only a gain of 2 after that point in time, right? And so if it's only a gain of 2, you know, a millivolt change on the input only makes a 2 millivolt change on the output, okay? So you don't have such a strong dependency after you put it into feedback. It's only when you're open loop and you have this huge amount of gain that you have to worry about getting this voltage, this input voltage exactly right. Okay. You know, changing the offset here is the same as changing the voltage there, of course. So use offset voltage in the early stages when you're trying to get your gain, so you make sure that you DC, so the output's at 0 volts, and you can working on your open loop response. And then in the end, you got to make sure, of course, that that's less than a millivolt, because that's one of the specifications. But for all process, okay. Now the other question was process variation. So we got a couple of different process files now. Okay, different spice files. What you need, how do you attack this? When you do DC biasing, do as much as you can to have things ratioed. I mean, have this. If you need to have some transistor needs to be biased at, you know, this is some sort of high swing thing, or something like that, right? So this needs to be at a VD sat of this transistor, right? And that means this voltage here, this is VD sat 1. Let's say this is transistor 1, this is transistor 2. This voltage needs to be at VT, okay, let's call this VDD. VDD minus VT of transistor 2 minus VD sat of transistor 2. And to put this voltage at a VD sat of transistor 1, you have to do minus VD sat of transistor 1. So if this voltage is equal to this value right here, then this voltage will be exactly VD sat of this transistor 1, which is right here. Okay. Now, how do you do this? Well, one way you could do this with a resistor string, right? You could, it's bad for all sorts of reasons, but it makes the point here. These resistor values have nothing to do with this VTs or these VD sats, and when you change the process, right, when you get a different value of VT from a different process, or a different value of VD sat because the K primes are different, this resistor string will have no way to adjust itself to compensate for that. On the other hand, if you make this out of some sort of transistor, okay, that's biased, like, somehow or other, right, then this voltage right here is a function. This will be VDD minus VT of this transistor, right, minus VD sats and so on. So if you make the circuit for your bias look like the circuit you're biasing, okay, then you can get everything to track. In fact, what you can go to an extreme in this. In fact, it's quite often done because of the problem of trying to set these bias voltages. It's called replica biasing. You can almost make a duplicate amplifier. Imagine this, okay? Duplicate amplifier, set the inputs to 0, okay, and pull off voltages off that amplifier to bias up your amplifier. Okay, you say, wow, that sounds pretty extreme. But, boy, it's difficult to get these voltages right. And I mean, the case I showed right here was fairly trivial, but sometimes when you have more complicated circuits, you might go to that extreme. You call that replica biasing, making a replica of your circuit and pulling the voltages off that replica with appropriate, where instead of having inputs, you now have just DC values. And you get DC voltages that kind of replicate what's going on in your circuit. And they're not a function of the input, and you can keep DC bias points correct. That's a more general approach to this biasing problem. We haven't talked about that too much here, though we've kind of implicitly done it. But that's something like in 240 you would do. Yeah.
How would you generate the bias voltages for the replica bias then?
Well, what you do is, let's say, what I do is just ground the inputs. The idea is to take the inputs. You don't have an input into the replica circuit, okay? Set those to 0. So then that circuit now sets up a bunch of DC voltages that you can use over in your circuit, right? There's not a function of the input values. Yeah, I mean, you're still, yeah, this doesn't solve the problem of some of you mentioned this. Good point. What about your final reference current that you start this whole thing from? Okay, boy, that's a function of a resistor or something like that and some VTs and so on. Yeah, that's true, and that doesn't solve that problem. You know, there's some, it's just a matter of making sure that you have all VTs cancel out. There's a replica of these VTs in your circuit, but there's a reference current that's establishing the reference currents for this and a reference current for this as well. Where does that reference current come? It's come from a lot of things. Sometimes what you can do is you'll bring that external. Okay, there'll be one reference current on your chip that somebody sets up with a precision resistor. Now, what it may be, you'll give your data sheet. You'll say, okay, put a 1% valued resistor between this point and ground, okay, and of this value, 10 k ohms. So you rely on some external, that 1% resistor, which costs 10 cents. Say, well, 10 cents doesn't matter too much. Well, it might matter a lot, actually. Okay, and sometimes you'd rather do something like that on chip, but then you have to make your design even more robust against all the possible variations that you have on your chip. And you don't have the option of asking for a 0.1 or 1% resistor, so you're going to have to deal with it on your chip design directly, right? You only have one amplifier, so it's a little easier. Yeah. Okay. Good. Okay, so like I say, you're getting a good practical. I mean, I think we've probably taken this project further this semester because you guys have actually been quite well in your other projects. I think it's really so you've been because you've done so well, you get rewarded. So I'm really happy how well the project's going this semester. So good. Not much left in the class. Next lecture, what I'll do is mostly a review for the final and take questions. So I guess it'll basically just be a final review, okay? And I'll talk about anything else you might want to talk about. Just so if we run out of things to talk about, we'll have a short class next lecture. So just bring your questions. So we'll make it a. I probably can. Let me figure out when a good time is. I'll have office hours, so maybe like I don't know. Let me check my schedule. Probably like Wednesday. That'd probably be a good day, right? Wednesday or what'd be a good day? Wednesday, Thursday, Friday, right at the end. Do you want to last minute panic questions, or do you want a little bit earlier so it's the They're up, right? There should be lots of projects. There are lots of exams up, right? Yeah, right. So you got lots of exams to look at, right? So I'll try to make it Wednesday. Okay, so I'll try to make it Wednesday. Maybe the same. Let me send some. I'll put on newsgroup.
Question.
Yes.
Is there a review for the final beside the lecture time?
Well, I'll do this little office hour thing. I think the TAs will probably do a review, right? So let's ask them, and I'll ask them to do it too. Okay, make sure this will have a another review. So get a review from me, get a review from them. Next lecture, you get a review. You'll be tired of reviewing for the final. Right? Okay, homework. This homework you have, if you don't do it, nothing's lost, right? Okay. If you do the homework this week, all it can do is help you. Okay. So that's the way to look at it. What I was going to do today was just give you a little bit of more strategy on how you deal with these circuits. And so let's just talk about.
Question.
Yes.
Is there any RF stuff in the final?
Yes. Possibly one simple RF question.
How many percentage?
7.3%. It won't be very much, and it won't be very hard. Okay. It'll actually be more just testing. The RF is just techniques that you should be able to use. I mean, that's basically the only new difference thing about RF, as we've shown so far, is you had an inductor, right? So it's basically using, to me, it's just kind of a review of techniques. And let me just say why I say that, right? Let me do this case right here. So as I mentioned last lecture, right, quite often what we do in RF circuits is you try to have, this is the antenna, let's say, and I told you it had effectively, it looks like a voltage source with a 50 ohm output impedance. If you remember to your maximum power transfer, theory, right, you should have, to get maximum power from a source to a load, you should have the same load impedance as you do your source impedance. This motivation of moving power from the antenna to the load has actually driven a lot of RF design in the past. It's actually not so relevant for CMOS RF design. And part of the reason is because one of the reasons what you do on a board is you try to make the lines themselves transmission lines that have 50 ohm impedance. So we're not going to talk about transmission lines, which is a different bit of RF stuff. But that's not relevant on a chip because the distances are so short, you're not looking at transmission line effects until you go to very, very high frequency, like 60 gigahertz. Then you look at transmission lines on chip. But until you get up there, it's not important. So this 50 ohm thing is a little bit of a carryover from the old days. And the other problem is that people design things. You don't have to design an antenna to look like 50 ohm. Actually, the air itself has a 300 ohm characteristic impedance. Okay, so 50 ohms isn't totally natural. It comes from a lot of history. Okay, but be that as it may, okay, there's a lot of issues there we can talk about, which we don't have time. You often want to have this input impedance here. Let's say if we wanted to have maximum power from your antenna to your load, which isn't always all the time the thing you want to do, but let's say you did, you'd like to have your load look like 50 ohms, and that's kind of what your project is all about. How do you make your load look like 50 ohms? Okay. Now, there's a couple things way you could do that. One is you could just stick a 50 ohm resistor right at the source at the gate. Okay, that would make this is your antenna over here, right? That would make your transistor, your amplifier, look like 50 ohms. The reason you don't want to do that is for this reason. Every resistor actually is a noise source. Okay, it's a thermal noise. Once you have a resistance, okay, you actually have random fluctuations. This is very low-level thermodynamics. I mean, there's just no way to get around this, okay? Right? The amount of noise you have in a resistor works out from very fundamental thermodynamic arguments. This has nothing to do with good resistors and bad resistors. This is pure resistance. Has to have a noise of 4 kTr. It almost comes from, like, entropy, right? I mean, you gotta, as soon as you have a loss like this, you've got to sort of have some randomness, and randomness is noise, and this is the noise power. Okay? The noise power is 4 kTr. Kt is the thermal voltage. Okay? R is the value of the resistor, and 4 comes from sort of some equal partition arguments. Okay? So the noise voltage is equal to 4 kTr to the 1/2. So this is the noise, the voltage, and basically you model it as a little noise source. Okay, and we usually think of noise power because it's a random fluctuation. Okay, it's in series with this resistor. So as soon as I add a 50 ohm resistor like this, I'm really adding a noise source here of 4 kTr. Okay, that's the power. Okay, of this little, or to 1/2, it's a little noise voltage in series with this resistor. So this is a noise that I have to deal with. Well, I can get rid of that. I don't have to do that. Okay, I can make this look like 50 ohms without actually adding a resistor. And that's your project. That's your homework, actually, to show you how to do that. Okay, and effectively what you do is, it's pretty interesting. It was, I don't know who figured that out originally, but it turns out if you put an inductor down in the source, this can look like 50 ohms, a real resistance, at the resonant frequency of this circuit. Remember, there's a capacitance here. There's a CGS here, right? So at the resonance of this circuit, where that, the 1 over root LC happens, okay, this can look like 50 ohms. And that's what you're going to analyze in your homework, how that happens. Now, I don't want to do that problem because that's your homework problem, but let me do something that's sort of similar, okay? Let me do this one. And you don't have to put a resistor here. So it's actually a noiseless way to make this look like 50 ohms, okay? That's pretty neat. So let's take a common source stage, okay, but let's not put this inductor down here because that's your homework problem. But let's do something else. Let's talk about how you analyze these circuits, okay? And it's just like we've been doing all year, right? So this is, let's put a series gate resistance in series with this C sub G, okay? And let's put, and then we can have our 50 ohms, and so if we're after the gain from V in to V out, okay, how would we do that? Okay, so what we could, for this circuit, what we'd want to do is, remember there's a capacitance associated here, good old CGD, because I haven't made a cascode here, okay? So we could put that down here, 1 plus CGD times, the gain of this stage, right? GM R load. And the question, what's R load of this stage? R load of this stage, for as I've shown it here, will probably be good old R0, looking like down here. But if we have this tuned appropriately, okay, what we'll end up with, actually, there'll be a series resistor associated with this inductor. It'll actually be that series resistor that we'll see at the tuned frequency, okay, right? So, or that related to that. But let's not do the tuned part. Let's just say there's a resistor here, R load, okay, in parallel with this. This capacitance here is associated with the parasitic capacitances on this node. This is sort of CDB, okay? And let's forget about CGD right now. Let's say we did a cascode to get rid of it. So we've kind of decoupled this input from the output. So that's important. Make this easy to analyze, okay? Let's calculate the voltage on this point right here. Now, as we go up in frequency, you would think what would happen is we got a little way we've been analyzing these circuits is we'd have this, let's call this CG, gate to bulk. Let's just call this C gate now, all that together, all the capacitance. I Miller multiplied this down, right? So all the capacitance, including the Miller multiplication of that. C gate, here's this 50 ohm thing, okay? So you'd say, well, geez, I have a time constant, a roll off on this input of 50 ohms with this C gate. All this capacitance on this node, including this Miller multiplied value. But what happens if I use one of these inductors right here? What I can do with that inductor now is I have let's calculate what happens at this point right here, VG. We really have a voltage divider between this capacitance here and this 50 ohm and LG, and so let's just write that. So V gate over Vn is equal to 1 over S CG, S is just J omega, okay, Laplace transform, okay. And we got a voltage divider. Let's call this RG here instead of 50 ohms. Just make it RG plus the drop across this SLG, which is the impedance of this LG, plus 1 over SCG. Okay, so this is the voltage divider. So this is the voltage I see at the gate, and it's just this voltage divider. Okay, well, let's multiply this out. Let's multiply top and bottom by SCG. I get 1 over S squared LGCG, okay, multiplied by SCG, plus S RGCG plus 1, okay. If we write this into a different form, let's divide top and bottom by LGCG. And we write this as 1 over LGCG, our standard form, quadratic. We get S squared plus S times RG over LG plus 1 over LGCG. Now let me give you a little. This is a kind of a standard form. This form here is a form of S squared plus S times omega naught over Q plus 1 plus omega naught squared. This is that form. In other words, if you get something in a form of S in the denominator, like this is 1 over this. If you get something, this is like the DC gain, right? If you, well, DC gain, this is what? S equals to 0, S equals J omega, right? That's when we evaluate this frequency response. So this goes to 0. So the DC gain of this is just 1, okay? Now, if you look at this form here, you can see that omega naught over Q is equal to RG over LG, and omega naught squared is equal to 1 over LG CG. And what is this omega naught and Q and all this sort of stuff? Okay, you plot that. So plotting this, it looks like this, okay? So at DC, the gain's 1, okay, for this circuit, okay? And that makes sense. At DC, what happens? The capacitor opens circuits, so all this voltage shows up right there. So it makes sense, gain of 1. Then what this thing does, it goes up and then comes down at higher frequency. As very, very high frequency, this is omega squared, right? So this thing falls off as omega squared. It's 2 poles. So this goes off in very high frequency as 1 over omega squared. Okay, because S goes as omega. This peak happens at omega naught, this number right here. So this is omega naught squared. So it happens at 1 over root LGCG. Okay. This width is delta F. Okay. And omega naught over Q is basically Q is equal to omega naught over delta F. So Q is actually how narrow this thing is. So this, as the Q gets higher, this thing gets narrower, and it peaks up more. This actually peaks up by a value of Q. Okay? It's a factor of 2 here, potentially. This may be 2 delta F. I'm not quite sure. Within a factor of 2, I'm right here. Okay. The point is, as Q gets larger, and what is Q equal to? Well, we can sort of relate, we can see what Q is here by setting Q is equal to omega naught divided by RG LG, right? And we know what omega naught is. It's root omega naught is equal to 1 over root LG CG to the 1/2. Okay, So I plug in omega naught here, and I end up with this being Lg over Cg to the 1/2 over 1 over Rg. Is that right? Yes. So this Q gets larger as this gate resistance is smaller. So you make this number smaller. But look what's happened here. This thing started off with a gain of 1. That's best case at DC. And it's actually gone up in amplitude. So putting this inductor here actually makes this have more voltage than it would have if we didn't have this little tuned circuit. Wow. This is pretty neat, right? I mean, in other words, what we can do by using these inductors, we not only get rid of the roll-off from this CG. I mean, this thing would have done something like this, right? At 1 over, I'm not sure what the bandwidth has been, 1 over RGCG. That would have rolled off like this. It actually went the other way. It actually helped us. We got rid entirely of the effect of CG and actually made this thing peak up. Now, that's really great. Can you use that in your projects? Sure, I'd let you have inductors, but it wouldn't help. And why doesn't it help? It helps because this is only true right around omega naught, right? It's because we're tuned to one frequency. All of this RF stuff, what's fundamentally different from what the circuit stuff we've been doing this whole semester, is that generally in RF circuits, you know, your cell phone, right, runs at around 2 gigahertz. Okay, it's you know, you start plotting stuff. This is 0. Here's a 1 megahertz. We're way up here at 2 gigahertz for these cell phones, and that's what we're interested in, only around that frequency way up there. So we can design circuits that are tuned to 2 gigahertz. If we had to have a circuit that worked all the way from 0 to 2 gigahertz, you can't use these tuned circuit approaches. These only work around some narrow frequency value. Okay. In fact, where do they work? Kind of in this delta F. As the Q gets higher, I mean, this thing's falling off like crazy. So it's only around very near where that tuned frequency is. Okay. All right. So that's kind of point 1. Point 2 is inductors kind of do all sorts of interesting things, right? Okay, like putting an inductor down in the source here, you're going to see this makes it feel like 50 ohms. Putting this inductor in this circuit right here actually tunes out the effect of this capacitor. Makes it so it's not important to us. Okay. Putting it up in the load at a resonant at the, if you look at this impedance of this RLC combination, you'll do this in your homework, you will see that you can choose a value of this inductor here that will tune out the effect of this capacitor. In other words, at the tuned frequency, this too becomes infinite impedance, and all you see left is the RL. And that's what you'll find in your homework. So inductors are really pretty neat. Now, they're about the same area as capacitors, and I mentioned that last to you. So they do take area, so they are costing us something, especially as we go to higher and higher, more scaled technologies. I mean, these inductor values are associated, with these parasitic capacitors, and so they're not going down as fast as we'd like, and so these conductors become more and more dominant to us. They're taking more and more area, and area is cost, right? So that's not good. So let me finish up the story here. Your homework problem is, let's say, looking into here, what is the impedance value? Well, how do you do that? Well, it's just like you always did it. All you're going to do, put in a test voltage or a test current and find the current into here. The only thing different is you're going to work now with impedances instead of with resistances like you did earlier in the year. But just put a test voltage, figure out the current that goes into this little parallel combination. You have, in your problem you'll have, an inductor down here, right? So you got to worry about the fact that V source isn't 0, right? It's GM times VGS is the voltage at V source is there's a VGS across here, right? So it's GM times VGS is the current, and you just got to solve that through, and just like we always did before. So the problem here in your homework is no different from what we did before, just has impedances now, and after you calculate these things, let S equal to J omega, and you can begin to see what happens. Okay, so that's kind of what I wanted to say. So anything more about RF stuff? I guess just let me say that it's a very interesting area now to work in. I think probably in 240 there'll be a lot more material on that. You've got all the ground rule. You got all the basic elements. Maybe what I'll do, I was going to do that, I forgot. I'll do it next lecture. There's a chip that 802.11a. This is for a Wi-Fi. This is 5 gigahertz Wi-Fi chip. We'll go through the circuits on that chip. It's on in your lecture on the website. Okay, it's the PDF is on there. We'll go look at those circuits for that. The power amp. I mean, the power amp. So what are the tough design problems? There's these first gain stages, these low noise amplifiers. You got to worry about these noise sources, not only of resistors. Let me just finish this up. Let's say this is your. Let's say it's a cascode. Okay. And we have a tuned load. Okay, so let's say this is your basic, and this is hooked to your antenna, right? Maybe there's an inductor here, right, to tune out the. So the inductors do not have any noise. Capacitors effectively have no noise. It's all reactive elements. It's only resistors that have this 4kTr noise. And transistors. Transistors have an effective resistance. It's one way to think about it, right? What's kind of the effective resistance of a transistor? What would you think it would be? Any guesses on that? It's kind of... This is kind of really rough thinking, but when we look up into here, what resistance do we see? Good old 1/GM, right? So it turns out there's a couple of noise sources associated with transistors, but one of them is a thermal noise, and so the noise of a transistor is equal to noise power is 4kT times some little gamma factor, a little fudge factor, times 1/GM. Okay, and this little gamma thing, because people don't really know what causes noise, right? So this is kind of the little factor that you kind of you throw in there when you do some modeling. It's like a third or, a half or 2/3, something like that, right? People can argue what this value is, but it kind of functions the process and the transistor size and the technology. But the most important thing is inverse proportional with 1/GM. So you can see what happens. How would you reduce the noise of a circuit? What would be the thing you would do? Induced 1/GM, so anything you really can play with. Reduce the temperature, that's pretty tough, right? And so 1/GM you can play with, so you'd want to put a lot of current through it. So actually burning current, using current power generally reduces noise, right? So that's kind of a trade-off. So if you really have a low noise situation, you often end up having to use more power to that. So we use power to have the circuit run fast. We also can use power to make the circuit be lower noise, right? So that's the LNA problem. Then you have a bunch of more gain stages. I told you about these mixer circuits, right, which are kind of cross-coupled differential pairs. Effectively, these mixer circuits look like you'll recognize them, right? They actually look like differential pairs. There's a bunch of different versions of them. But one version, okay, is you put, a signal in across the differential pair, right? And you put another signal in down here on what we'd call the current source, okay, V2. Okay, here's V1. And you work this out, it turns out that the signal you get at the output here, right, okay, is sort of the product of V1 times V2, okay? So that's, you've sort of seen this circuit before, okay? And there's other cross-coupled ones that are actually even more efficient than this thing is. But this is the kind of idea what you do. You sort of put in circuits you've seen before, but you put two signals into it, and you'll end up with some sort of product on the output. Okay. So that's the mixer. I mentioned to you mix down from high frequency to low frequencies. Then there's the bass. After you mix down to lower frequency, then you go into the baseband circuits. And that's what you've been designing all this semester, is the baseband circuits. The circuits that work across 0 to 20 megahertz, not at 2 gigahertz, but 0 to 20 megahertz. And there'll be some filters and things like that. And I'll show you what a filter looks like next thing in a few minutes. But you do a filter to reduce so you don't get any of the higher noise from. If you got your cell phone at 2.4 gigahertz, when you mix down, you might have some other noise sources mixed down as well, coming from TV or something like that. Well, you got to filter that stuff out. Well, we'll do that at baseband circuits that you're doing. We've done. Then there's the other big challenging circuit is the power amp driving the antenna. So the antenna kind of looks like 50 ohms. So you know what this problem's all about. You had to do this in your first lecture, right? You got to drive. We mix back up to 2.4 gigahertz, and we got to have an amplifier which drives this antenna up at 2.4 gigahertz or 5 gigahertz or 1.9 gigahertz, depending whether it's a cell phone or a Wi-Fi chip. And so how do you do this power amp? Well, I'll show you, but you guys know it. I mean, you've looked at, it'll be very similar circuits to what you've seen so far. You can use inductors to sort of tune out capacitance as much as you possibly can, but you still end up with basically having to drive 50 ohms, and you know how tough that is, right? And so, okay, so I guess just summary. There's a good, I think on the lecture, if you're interested in this topic more, okay, your Christmas reading if you'd like, right? Right. The book by Lee, where's my first name right now, over at Stanford, is a nice. It's a paperback, so it's a little cheaper than usual, but it's a nice, easy reading book. I mentioned it earlier, in the sense that it covers a lot of the same topics we covered in this course, but he threw in some of the RF stuff, and also what he does, which is pretty nice, is he talks about history a little bit. It's kind of why it's easy reading, because it's a little bit humorous, and he kind of talks about, I mean, if you find humor in, this is real engineering stuff, right? You find humor in sort of building, sort of designing circuits and what's happened in the past and so on. But it is kind of fun, and so it's a nice. After this course, you can read big chunks of that book, and it'll be easy for you to go through it, right? And so, I recommend that. What is his first name? Blank. Okay. I'd say just the sort of final topic on this RF stuff, except for I'll do next lecture a little bit, is probably the into the future right now. I'd say, I mean, one of the really interesting areas is this RF design, because CMOS is just beginning to grab more and more frequency bands. So I think understanding baseband design like you know now, understanding RF design, you've really got a set of skills that's a very sellable one. So, okay, so let's shift gears a little bit. We started talking about the other big. Now I'm talking about the baseband circuits. You get this, if it's an RF circuit, you get it down to lower frequency. If you're doing a sensor network, it's amplifying the transducers in a sensor network. If you're doing, I mean, just about anywhere where Paul Gray, your chancellor, used to give a talk all the time, right? And he talked about the world. Here's the digital world. Okay, this is the world of microprocessors and dedicated ASICs and stuff like that. Here's the real world, okay? Here's where we live, okay? This is the world of, temperature and heat and cold and sound and things like that, okay? Quite often the job is to get from the real world into the digital world, do some processing, and then come back out to the real world again, because we live out here, right? This is us out here, right? We're happy little people out here, right? Okay. So how do you get back and forth between these two worlds? Well, what he used to call about is a little skin. It's a little teeny layer that wraps around this digital world. And that's us. That's this class, right? We're this little skin. You can't directly go from talking right into a chip, right? You got to do some A to D conversion. You got to do some filtering. You got to do some amplification. You got to do all this stuff. It's this skin that we do. But boy, is it critical stuff, right? Okay. A lot of the things you need to do there, the really core ones, is amplification. And that's what you've done a lot in this. That's what this course has been majorly focused on. But the building blocks of amplification are also used for filtering. They're also used for A to D and D to A conversion. Okay. They're also used for mixing and some of these other things you have to do in the RF world to get things done. So let me talk about the basic techniques we use quite often around filtering and A to D and D to A conversion. Okay. So let me do filtering first. So what do we mean by filtering? Filtering, as you know, I mean, the typical problem is this. We have, some transducer of some sort, microphone, let's say, okay? You need to filter it, band limit it, okay? And then you go to the A to D converter, okay? So all of this, then you go to the digital stuff, okay? This filtering function, before A to D conversion, if you're taking 120, you know you've got to band limit the signal to 1/2 the bandwidth of the A to D converter. Typically, it's a mix of filtering and amplification that you do, because you want to amplify a little bit and filter a little bit and amplify a little bit. So how do we do these filters? I'm showing this as a low-pass filter. So what I mean by filter is that as a function of frequency, that we'd like it to, if it's a low-pass filter, we want it to go out, and then at some cutoff, okay, low-pass filter cutoff, we want to design it so it falls down, drops off as fast as we can. So it's like our compensation problem in a way. But we want to make this really sharp. We'd like to have this thing fall off, maybe like 1/1 MB/5 or something like that. I mean, lots of poles. And we use zeros as well as poles to make this thing fall off. Okay, if we put a 0 near that edge, that a 0, it goes to 0 at 0, right? And so we can place that as close as we can. It'll drop this response as fast as we can. We don't want to have this tail off like this, so we put some poles in quite often to sort of keep this up. So there's a filter design problem associated with poles and zeros. Well-solved problem. There's programs that do this. MATLAB has good programs that do this. You can give about any filter spec. It'll pop back with the poles and 0 locations that would give that filter response spec. Okay? So now, our job is, how do we design circuits that create these poles and zeros at arbitrary location? Your problem right now in this op-amp thing is to, kind of move these poles around 0 around a little bit. Our basic approach will be to take your op-amp that's stable, put feedback around it so that we can create poles and zeros at particular spots. And that turns out to be real easy to do. Okay? So how do you do it? Okay? See how easy it is? I can go through notes so fast. I want to get to a certain picture here. Well, let me just skip to that. Okay. What we'd like to start off with is something that looks like this, okay? And this looks pretty familiar to you, okay? This is a circuit like this, okay? Okay, let's just take this RF and RN. So this is kind of like what your project's all about right now, right? Let's say we take this circuit right here, and let's change this a little bit. Let's put a capacitor, okay, right across here, for example. Okay? So can you tell me, just sort of intuitively, what's going to happen with this circuit as I go up in frequency? This is CF. Any ideas? What's going to happen as we go higher and higher in frequency? What's the gain of this? Before I do that, let's just start with the gain of this. Before I put the capacitor there, what is the gain of this circuit? V2 over V1, you should know now, is minus RF over RN. Okay? So now what's going to happen to this circuit as we go up in frequency? Gain gets less, right? What I can do is replace this here, instead of just by RF, let's make this now equal to minus ZF over Rn, okay? That's all you have to do. I mean, impedances are just like resistances, they satisfy the same Kirchhoff laws, right? So it comes in the same way. So as we go up in frequency, what's going to happen? This capacitor is going to get to be a smaller and smaller value, okay? Finally, it's going to be a short between here, and that's like having RF equal to 0. So this gain is just going to get lower, smaller, and smaller as we go up into frequency. So what does that mean? So what's going to happen? At high frequency, this thing is going to fall off. Well, let's just plug in the numbers here. ZF is really the parallel combination of CF and RF, right? So that's 1 over j omega CF, I'll use j omega instead of S this time, times RF over RF plus 1 over j omega CF, okay, all over Rn, okay. So I can take this, and let's get we want to get into our standard form. So what is our standard form? It's the 1 plus business. So let's take RF over Rn out front, okay. Let's factor down front here. And let's top and bottom by 1 plus j omega CF, and I end up with 1 over 1 plus j omega RF CF, okay. And this, we know, is basically 1 over 1 plus j omega over omega p. So this is, the pole for this thing is 1 over RF times CF. So I can take this op amp that you're going to make nice and stable for me, okay, right? And what's going to happen is that, notice what's going on here as we go up in frequency too, right? What's happening? We're getting more and more feedback, right? All right, so we're going to have to make this circuit stable against the situation we have basically feedback of 1 across here. We're just feedback all the way. So that's kind of why you have to sort of often work by the worst case stability condition. And we can sort of view this as a block now, and that's kind of how you want to do this. The circuits you've been designing are just a building block. It's stable. We don't worry about it. It has nice transient response results, that's what you're working on right now. And then we can start putting inside circuits like this to control where we put poles and zeros. If I want to do 2 poles, I can put another stage after this, right? I can do all sorts of other things too. You can put capacitors down like this, and it changes it. You could have one amplifier like this actually have 2 poles by itself. I mean, this is kind of 1 pole per amplifier. It's actually fairly easy. There's lots of circuits that have 2 poles with using 1 amplifier. Okay, and you can put a resistor capacitor combination here on this node here, and there's all sorts of things you can do to make. And there's just a big literature. We call these active filters. This use of op amps and resistors and capacitors. Why don't we use inductors? Because this is generally at such low frequency. Baseband inductors will just be way too huge. So it's just usually R's and C's that we deal with. So these are active RC filters, what we call them. Okay. And what they replaced a long time ago was the way people a long time ago had to do things. They used real inductors and capacitors and put them together in ladder networks and stuff like this to make filters, okay? And here's a big step. I'm not going to have time to really go into it in too much depth with you. But in actual fact, much of our filter design that we do, I told you we can place these poles and zeros in arbitrary places. There's lots of different structures to do it. Turns out some of the best structures are actually ones where we do effectively a simulation of this LC networks, okay? So basically we can take op amps like this. If you look back in literature, there's a period of time when people did analog computers, and what they did was they used op amps, effectively, things like this, and sort of modeled the differential equations associated with things like this, LC networks. So what you do is this node here, instead of representing a voltage, would actually represent a current, maybe the inductor current. And there's a much more complicated structure that you put these things together. When you do that, you can model these LC networks and actually have very good characteristics. And so that's often done. In fact, digital filters, even yet, are based on, to a large extent, the analog LC-like networks quite often, because they have better characteristics. So this is all to do with filter design. I guess 126, does that do filter? Is filter design done in there, right? 123. I used to do a lot of filter design stuff there. There's a huge amount of literature. Fortunately, you don't have to do too much because it's all inside of programs right now. I mean, like I say, MATLAB, you can go in there and they can just fiddle around with poles and zeros and these kind of structures like crazy. Okay. That all being said, you got the basic building block to do this stuff. Now, What's wrong with this approach right here, this RF-CF thing? If we want to put this all onto a chip, so the pole was at 1 over RF-CF. If we want to do a fully integrated active RC filter on a chip, what's the problem? What are problems? You're practical designers now. I tell you to do a filter, and I want that filter to run at audio frequencies. I want it to roll off at 40 kilohertz. And I want it to be as cheap as possible. How would you do it? Would you put everything on chip? And if not, why not? Okay, designers, come on. This is your chance. Next person's asking you, this is your boss. Okay, right? So your next raise is dependent on, do you do a good decision here, right? So what would be your answer? He says to you, or she says, I want a filter that rolls off at 40 kilohertz. You said, okay, I know how to design that. I'm going to take the circuit right there, okay, right there, all right? And you're going to stick it all on the chip. How big a chip is it going to be? Very big, right? Because what's going to happen? You're going to have to do this time constant on the chip, right? So what's a reasonable size capacitor? A reasonable size inductor. Let's take resistor there. Reasonable size resistor is what? Megohm? That's pretty big, right? Megohm resistor? So let's take a megohm resistor. Let's say we want to have this equal to, let's make it 10 kiloradians per second, okay, just to make it a 10 kiloradians per second. So mega P is equal to 10 to the fourth, okay, radians per second. Let's say that's our spec. That needs to be 1 over a megohm times the capacitor. So C is going to be equal to what? It's going to be 1 over 10 to the 6th times 10 to the 4th. This is 1 over 10 to the 10th, or 100 picofarads. A megohm resistor is not small. A 100 picofarad capacitor is just huge. Okay. Do you have the numbers for size of capacitors on your project? I don't think you do you? How are you going to get area? What are numbers for size of capacitor? Well, you can think about, I should get you some numbers on that. But it's like, let's say, geez, I'm kind of, I'll give you some numbers next time. I got to do it in modern process. I can only come in old processes. 100 picofarads is big. Let me take my word for it. We're talking a chip full of capacitor in that case, right? This is not going to fly. And a megohm resistor is not bad either. What's another problem? So area is a big problem. What's another problem? How about accuracy? If that resistor is going to be plus or minus, let's say, 20%, and the capacitor is plus or minus absolute value 20%, what's your corner frequency? Plus or minus like 40%. So not only did you use up a whole chip, you didn't even get the right answer. So, what can we do about that? And here, let me just, the problem is the resistor, okay? The problem, let's say we want to, the problem is dealing with this resistor, this absolute value of resistance. There's a circuit that we can replace this resistor by and get effectively the same value of this resistor, but not use a real resistor. And what is that circuit? Let me show it to you. It's this. And let's take this into, there's all sorts of things. Okay. Now, of course, there's all sorts of, so what is this little thing right here? This little thing right here, the real circuit of that is this. It's two switches that go between, and we don't even actually know what the source drain. They're actually operated off and on, so that identifying what is. So this circuit right here is a circuit like this that has two clocks associated with it. So this is a clock. So the two clocks like this. And what clock, what I mean by that is it goes between 0 volts and 1.2 volts. So what happens is this transistor slams between being cut off, or let's do it between minus 0.6 and plus 0.6. And let's say this is nominally around 0 volts. So this switch is either shut off, that's when the switch is in this, or when the switch is over in this position. So this would be the shut off. So this is like a double pole single throw switch, okay, right? So in other words, this switch is on when the voltage on this is high, it's plus 0.6, and this would be off at 0.6. Then we switch it. There's another phase of this clock. It goes like this. So when this switch is off, this one's on. When this one's on, this one's off. So we alternate between having this switch in this position or in this position. Okay? So what's that all about? Okay? So here's what that's all about. So let's just look at what's going on here. Now notice the important thing here is everything's just capacitors, no resistors. If we have two voltages here, how do we figure out what the effective resistance of this thing is? Well, we do like we've always done. We can sort of, let's say, let's just ground this one. And let's put this as our test voltage on this side. Okay? So let's figure out what current goes into this circuit. Okay? Well, when this capacitor is on this side, it charges up. We have to look at charge on this node here, Q on C. So this is a really different kind of thinking. The charge on this node is QC, and what is it equal to? It's equal to V1 times this capacitance value. When that switch goes over to this side, it discharges. Well, let's leave it to V2. Okay, let's leave it to V2 just so you can get the whole point. Leave it to V2. So this is sort of on time 0. At time half the clock over 2, I mean this clock has, at half the time period, right here, okay, this is TC over 2. This is time t equals 0. This is time TC. So this is the clock period, okay? This thing becomes equal to V2 times C, right? Because it discharges into this capacitor, right? So there's been a change of charge on this capacitor. When I come back again, I'm back to up to V1 times C again. Well, how much charge do I have to provide into that capacitor? Well, it's the difference between these two values right here. So the delta Q I have is equal to C times V1 minus V2. I have to provide that much charge into that capacitor. If this was equal to V1, there'd be no charge into here. If this is a different voltage, we'll have to provide that much charge in the next time period. So this is at TC. So I'm going to have to do is every clock period TC I have to provide this much charge. It's kind of pulsed, but forget about that for a second. So what's current? Current is charge over time. And time in this case, delta T, okay? And time in this case, every delta Q I have to provide, it happens every TC. So the current is equal to delta Q over TC. And delta Q, I said, was C times V1 minus V2, okay, over TC. If you look now, I got current equals V1 minus V2, so V1 minus V2 over the current, this is the test current, basically, this is the test voltage applying, the differential voltage across this, okay, is equal to 1, is equal to TC over C, or 1 over FC times C. FC is the clock frequency, 1 over the clock period. So this is the resistance of this circuit. So this circuit acts like a resistor. Now, so if I have these kind of resistors, which is proportional to this, so that's the R, it's equal to 1 over FC times C1, let's say. let's say I want to have this, let's make this is C1. Let's make this C2. Our time constant was this R times that C, right? So what's that equal to? RC here is equal to 1 over FC times C1 times C2. So this ends up equal to C2 over C1 times FC. So this time constant, which sets the pole location, is now a ratio of capacitors. Wow, that's pretty neat. We can set the clock frequency, we can set the ratio of these two capacitors, and we can get precise time constants. Doesn't have a huge capacitor. The area is very small, actually, because these capacitors are only ratioed. We don't have to make them big because there's no absolute value concerned. This whole idea here is based on switch capacitor filters. So you can build this thing up and you can do all sorts of fancy circuits. I have a picture of one here. So it can look like this. This is a portion of a switch capacitor filter. And these are all the switches, and you put them on the bottom plate instead of the top plate and all that kind of stuff. But the core of this circuit is these op-amps, and that's what you've been designing. So basically, you take our op-amps you've done in this course, you throw around some stuff like this. This only drives pure capacitance. You know, that's much easier to do than driving resistance, right? So that's another big win for this. It's a pure capacitive-driven circuit. And you can make really complicated filters, just arbitrary complexity. This idea of using capacitors and switching and stuff like this is actually the base of a lot of A to D and D to A converters. So you, again, only have to drive pure capacitance. But that's kind of, I guess we do this in 247.6. Boser teaches a bunch of this stuff, right? You know, this kind of thing, right? But you've really got the core here. This other stuff actually a lot easier. Most of the design work goes into this. This stuff here is pretty straightforward to do. Okay, supposed to do is the guy here? Okay, yep. So we're going to do the Ada Kappa Nu thing, and I'll zip out of here. Are the homeworks that we passed around? Let me pick those up. I'll pick them up in the back there. Okay, I'll bring them here, Jim. I'll see you next lecture on